Hello everyone, today we are going to be talking about thermal processes of solids and liquids. So I just want to give a very brief introduction to what Q is in this equation. We are discussing the Q equals MCAT equation here. And Q is a measure of heat transferred into or out of a system. So simply put, if we are considering, let's say, a beaker of water, Q is the heat energy that would be transferred in or out of the system. So Q would be the amount of energy input into the system. So let's say like the energy from a fire underneath heating up the beaker of water. Or it could be the measure of energy lost to the environment, so negative Q. So a positive Q would denote an increase in heat energy, energy being put into the system. And a negative Q would be denoted by heat being lost by the system. And of course, this is in the units of joules because Q is a form of energy, heat energy. And if we want to just break down this whole equation by units, we can say that joules are equal to kilograms times, and for temperature, we can keep it in either Celsius or Kelvin, but for this case, I'm gonna put Kelvin for simplicity, times Kelvin times joules over kilograms times Kelvin. So as we can see just by the units here, kilograms cancel and Kelvin cancel because kilograms divided by kilograms would just equal 1 and Kelvin divided by Kelvin would just equal 1, leaving just energy on both sides. And I want to make a note of what specific heat is. The specific heat is unique to a given substance, and it denotes the amount of energy needed to increase 1 kilogram of a compound by 1 degree Celsius or 1 degree Kelvin. And I'm using Celsius and Kelvin interchangeably because the amount of energy required to increase something by 1 Kelvin is the same as the amount of energy required to increase a compound by 1 degree Celsius, because these are technically in the same scale. The difference between these two systems of temperature measurement is that Kelvin is an absolute measurement of temperature, meaning that 0 Kelvin is when there is exactly 0 energy in the system, whereas 0 degrees Celsius is simply the temperature at which water freezes, but there's still energy within that compound of like frozen water. So if I were to, down here, just graph out temperature versus energy in the Kelvin system, so if this is energy and this is temperature of Kelvin, in the Kelvin system, 0 energy would be denoted by 0 Kelvin, whereas for the Celsius system, 0 degrees Celsius still has energy, and we have to go until we're at negative 273.15 degrees Celsius for us to have 0 energy in that system. So that's why we can use these units interchangeably, is because an increase in 1 degree Celsius is equivalent to an increase in 1 Kelvin. So with that being said, when you are using this equation, be wary of the changes in temperature, specifically because if it's in Kelvin, you want to keep it consistent with units of Kelvin for specific heat. And likewise, if it's in degrees Celsius, you want to keep that consistent with degrees Celsius. And with all that being said, let's get started on these questions. Okay, so for 5-17 quiz question 1, a fixed quantity of heat is transferred into a sample of some substance. The sample is not at phase transition temperature, so this is important simply because it helps us denote which equation we are using, which is the Q equals MCAT equation. In which of the following scenarios would the sample be most likely to experience the greatest increase in temperature? So I went ahead and wrote out A, B, C, and D because I want to create 4 hypothetical scenarios. And I also rearranged the Q equals MCAT equation to solve for delta T, or temperature. So we can see that temperature, the change in temperature, is inversely proportional to both the mass of a compound, and it is inversely proportional to the specific heat of a compound. So given that information, it's safe to say that as the mass of the object increases, the mass of the compound increases, the change in temperature decreases. And likewise, as the specific heat increases, the change in the temperature decreases as well. And we can reverse this. As the mass of an object decreases, the change in temperature increases. And if the specific heat is lower, then the delta T, the temperature, is greater as well. So if we have a fixed energy, so we're going to just create random numbers here. So for this question, we're going to say Q is equal to, let's say, 1,000. A large mass would be equal to 10 kilograms. So this is mass sub large, mass sub small, because we have cases of masses being large and small. That's equal to 1 kilogram. And then specific heat capacity, we'll say the large specific heat capacity is 10 joules divided by Kelvin times degrees Celsius, or times kilograms. And the small specific heat is equal to 1. Simply, we're just using these numbers because they're easy to do mathematically on the fly. So plugging all this in, for A, it's saying the mass of the sample is large, and the specific heat capacity is large. So delta T is equal to 1,000. So we're using that fixed energy input into the system that's mentioned in the problem, divided by mass, which we said the large mass would be 10 kilograms, times the large specific heat capacity, which we just said is 10, and that comes out to a change in temperature of 10 degrees Celsius or 10 Kelvin, depending on the units that you input. Comparing that to B, where it says the mass of the sample was large and the specific heat capacity was small, we can say that delta T equals 1,000 over, we're using that large mass again, 10, as our arbitrary values, times our small heat capacity, which we just said is 1, and that's equal to 100, a change in temperature of 100 degrees Celsius. And we see that B is already larger than A, meaning that A is false. A is would not yield the greatest increase in temperature, so A is false. Going on to C here, we see that the mass of the sample is small, so we're using the small mass sample, but the specific heat capacity is small as well. So we're using both of the small values that we arbitrarily assigned for this example. So delta T equals 1,000 divided by 1 kilogram times 1 joule divided by kilogram times Kelvin. So we're just going to put a 1 there. And simplifying this, we see that the delta T for this hypothetical arbitrary compound is equal to 1,000 degrees Celsius, or 1,000 Kelvin, or 1,000 Kelvin, depending on the units that you use. And just before we knock out part D, let's just put it into the equation here. Delta T is equal to 1,000 divided by, and we're using the small mass quantity, so 1, times the large heat capacity, so we're using the 10, and that's equal to a delta T, which is equal to 100 degrees Celsius, or 100 Kelvin. So we can see here that part C, that answer choice C, has the largest change in temperature. And sometimes it's very useful to put in these arbitrary values because it helps visualize the answer choices that are given. Because without it, you might be thinking in your head, well, you're trying to create too many scenarios in your head and you get lost in all of the specifics. But having arbitrary values written out, you can see, clearly C is the answer because we have the greatest delta T. So utilizing these equations and knowing how to manipulate them is very important in order to get our correct answer choice. And yeah, with that being said, let's move on to the next problem. So 5-17A states, 2 liquids A and B have equal masses and equal initial temperatures. Each is held for the same length of time over identical burners. Afterward, liquid A is hotter than liquid B. which has the larger specific heat. So let's break this down. We're going to say that this is A and that this is B. And we know that for both of these scenarios, the heat transferred into A is equal to the heat transferred into B. And we know that the mass of A is equal to the mass of B. So for each of these scenarios, we also finally know that the temperature of A, denoted by this last statement here, is greater than the temperature of B. So again, we can plug in just arbitrary values for each of these in order to solve for specific heat. So this question is asking us which one has the larger specific heat. And we can approach this in two ways. We can simply say, denote the relationship between temperature and specific heat. Specifically, recall that temperature, delta T, is proportional to 1 over the specific heat. So if temperature is higher, the specific heat is lower. So temperature, liquid A having a higher temperature means that it has a lower specific heat. But we can also approach this using arbitrary values. So we could say again, the amount of energy transferred into both of these systems is 1,000 joules. And we can say the mass of these are both 1 kilogram. So 1,000 equals 1 times some value C times, and then this is the part where we get to input some value of T for both A and B where they're different. So let's say that liquid A increased by 20 degrees, whereas liquid B only increased by 10 degrees. So simplifying each of these out and solving for C, we see that 20 times 1 is 1, and then 1,000 divided by 20 is 50. It is 50. 50 equals C. So that would be, writing out all the units, it would be 50 joules divided by kilograms times Kelvin. Whereas in answer choice B, when solving for C, we get 100. 100 equals C. So 100 joules divided by kilograms times Kelvin. So given all this information, we can see that liquid B has the higher specific heat and than liquid A, because it had, for the same amount of energy input, it had a lower change in temperature. It takes more energy to get to the same amount of temperature change as liquid A. And that's why B is the answer. And we approach this again from two different ways. We can just look at the proportionality between the two variables. So delta T is proportional to 1 over C. So as the change in temperature increases, the specific heat for a constant energy, the specific heat of that compound must be lower. Or we can approach it by including arbitrary values to solve for C, given the information that is presented to us. And it's, as I've said, it's important to understand that we can do these problems in multiple ways, because it helps us approach novel problems when we're not sure what we're looking for in a specific problem. But with everything being said, B is the answer because for a given amount of energy, it does not increase in temperature as much because it has a higher specific heat. For the final problem we have here, we have 5-17b. 1 kilogram of silver with a specific heat of 234 joules per kilogram times degrees Celsius is heated to 100 degrees Celsius. So it has a delta T equal to 100 degrees Celsius. It is then dropped into 1 kilogram of water with a specific heat of 4,190 at 0 degrees Celsius in an insulated beaker, so that there is no heat transfer. After a while, the common temperature of water and silver is ... So, for this problem, since we know we have no heat transfer, we know that the energy input into silver, the energy input when it is heated to 100 degrees Celsius, is going to be the same as the energy transferred from silver to water when it is placed into that beaker of water. So we can find, based on the given information, we can find the amount of energy of the silver after it was heated to 100 degrees Celsius, and then we can use that information to find the change in the temperature of water as a result. So with that, I think it's easier just to start using the equation Q equals MCAT and plugging in the variables to solve for Q. So Q is equal to 1 kilogram times 234 joules divided by kilograms times degrees Celsius times a delta T of 100. And we see that Q is equal to 23,400 joules. And that's the energy of the silver. That's the energy, the heat energy added to the silver to get it to 100 degrees Celsius. Now, when it's placed in that water, it is transferring that heat energy to the water, and only to the water, because we see that we have an insulated closed system here. So we can say that the energy added to the water is equal to the energy of that silver. So we can say that 23,400 is equal to 1 kilogram of water, so 1 kilogram of water, times that specific heat of 4,190, times some delta T that we don't know of yet, because that's what we're solving for. It's asking us what that common temperature would be, what that delta T of the water would be given this additional energy added to the system. So solving for delta T, we get that 23,400 divided by 4,190 is equal to, so delta T is equal to 5.58 degrees Celsius. So the delta T of water would be an increase of 5.5 degrees Celsius from 0. So 0 plus 5.58 is equal to 5.58 degrees Celsius, meaning that B is the answer. Now, we could have approached this also a different way. We could have seen that the relationship between specific heat and temperature change, it will be proportional. So we could say that the specific heat times the delta T of the silver is equal to the specific heat of water times the delta T of water. So we could plug in these values and say that 234 times 100 is equal to 4,190 times delta T of water. And we can solve for delta T and get that same answer. And we just remove the variables that are constant. So, as I've been stating throughout this video, it's important to approach these problems from multiple avenues because it helps us really understand these equations. And as I've stated in my previous video on power, understanding the units of these equations helps us to manipulate them in a way to ensure that we are getting to our desired answer. And with all that being said, E is not the answer because that's the change in temperature of the silver. D would be the case if the specific heat of water was way lower. Same with C. And then A would be the answer if the silver was just not added into the system. Because there would be zero energy change of that water at 0 degrees Celsius. So that is why B is the answer. And then we went through, with each of these problems today, we went through and solved them in two different means. Really focusing on both the quantitative aspect as well as the proportionality aspect of each of this equation. So hopefully you found this video helpful. If you did, please leave a like on the video and have a great day.